in the second part of chapter 10, we're going to discuss angular momentum. Angular momentum is one of the 5 quantities in physics that are always conserved. Those would be mass, energy, linear momentum, angular momentum, and charge. Okay? So today we're going to look at momentum. Always easy to start with, how does it work for linear motion? Linear momentum, which was represented by that lowercase p, who knows why, is a vector quantity, mv. Of course, if you remember, it had an SI unit. That was simply kilograms meters per second, and it was a vector quantity. Similarly, angular momentum is represented by a capital L. I have no idea who picks these. And of course, instead of mass, we have to use our moment of inertia. And instead of a linear velocity, we will do an angular velocity. We haven't really talked about what the directions are other than to say that we consider counterclockwise to be positive and clockwise to be negative. Well, actually, we may have briefly talked on this. If you have something rotating counterclockwise, the actual direction is considered to be out of the board for the vector. Okay, we use that right-hand rule. If it were to be rotating the other way, again, take your right hand, you rotate the direction. Now you can see that that vector would point into the board. What about units? Well, the moment of inertia is a kilogram meter squared. And angular velocity is usually radians per second. But of course, a radian is not an actual unit. So really, it's just per second. So we end up with kilogram meter squared per second. So similar, except that we have this extra value right here. This extra meter in there. Let's look at an example. I'm going to erase this to have a little bit more room. I believe this is example 10.7, but it's about a mobile. You remember making mobiles for solar systems and planets or art class. And this is a really simple mobile. It consists of a long rod and on the end of this rod are two 2-kilogram masses. Now, it's going to rotate where it's suspended at its midpoint. So we've got some kind of string, so it's free to rotate about its midpoint. All right, we are not going to ignore the rod in this case. We're going to take into account the moment of inertia of the rod. The rod, it says, has a mass equal to 3 kilograms, and it has a length, which is usually an L, that is 40 centimeters. If you look in your book, besides moment of inertia for cylinders and spheres, there are 2 different formulas for moment of inertia for rods. One for when it rotates about the center, and one for when it rotates about one endpoint. So in this case, it's rotating about its center. So for the rod, the moment of inertia is given by the formula 1/12 mL squared. So we have 1/12. Our mass is 3.0. Our length, which which they gave in centimeters, we'll need in meters. So that's going to be 0.4 meters squared. So just for the rod, we calculate that comes out to be 4 kilogram meters squared. For the two masses on the ends, these were 2 kilogram masses. We just use the fact that I is equal to mr squared. And of course we have 2 of them, so we multiply that by 2. The length was 40 centimeters. So the distance here for this r, which is from the center of rotation, would be 20 centimeters or 0.20. I'm sorry, I did make a mistake. This is not 40 centimeters. I misread my own handwriting. It's 4 meters. Let's fix it. 4 meters. So this was not 40. It was 4. However, my answer was right because I just looked at my answer. So that is correct. If this is 4 meters long, then r is 2 meters. So there's mr squared, and then there's 2 of them, so I multiplied it by 2. That comes out to be 16 kilogram meters squared. So the moment of inertia for this whole system is going to be that sum. So this system we worked out had a moment of inertia of 20 kilogram meters squared. And I apologize for that confusion on this being 4 meters. But that makes that sense. This is, like I say, if it helps, I could have done them each mass separately. This 2 kilogram mass is mr squared, so 2 times 2 squared plus this one also is 2 times 2 squared. That's where we got the 16 for a total of 20. All right, so we understand how to get the moment of inertia of some type of system where we have to kind of piece together the different parts. Okay. They tell us it is rotating, it's spinning with 3 revolutions per minute. So I need to get that in radians per second. So I have 3 revolutions, 1 minute. I know that there are 2 pi radians in 1 revolution. Also know that there are 1 minute is going to have 60 seconds. Notice this kind of comes out nice because that would be 6 pi over 60 or pi over 10 radians per second. Now, I can't have final answers that have pi's in it, but I can certainly have pi's for in-between answers, especially since that saves me from having to worry about rounding and significant digits. So this is omega. So if I want to calculate the angular momentum of my system, L is simply going to be I omega. I was 20. Omega was pi over 10. Now I do want to go ahead and round that, and that comes out to be 6.3 kilogram meters squared per second. The other thing they asked me to do in this problem, besides calculating the angular momentum, is to calculate the kinetic energy, which in this case is all rotational kinetic energy. That's, of course, given by 1/2 I omega squared. I is 20. Omega is pi over 10. And my kinetic energy comes out to be 0.99 joules. Okay, angular momentum is conserved as long as there is no external torque, just like linear, linear momentum is conserved if there's no external forces. What's that mean? That means that your initial angular momentum has to equal your final angular momentum as long as there is no external torque. An external torque, of course, would be a torque that was applied by some object outside of the system, which would require both a force and a lever arm, because remember, if the lever arm is 0, there's no torque. Or if the torque is applied so that you get that sine phi equals 0, there's still no torque. So we'll look at that. In this case, we've got 2 discs on an axle. This is example 10.8 out of your text. In the initial kind of before picture, we've got a larger disc and a smaller disc. They're both on a common axle. That is ideally drawn right through the center. I didn't draw it perfectly, I know that. So this has moment of inertia A. It's traveling at an angular speed omega A. This has a moment of inertia B. It's rotating with an angular velocity omega B. So we have these 2 flywheels. They have different masses and radiuses, so we know they have a different moment of inertia, and they are revolving independently. One could even potentially be at rest. Afterward, something happens, and these are now joined like this. We have got the larger disc and the smaller disc are now in contact. Here's our axis. In other words, they stuck together. It reminds me of an inelastic collision where you have 2 different masses, and after they collide, they're now stuck together. So this will be rotating with a new omega. If we think in terms of, and this, we don't have any numbers, but it wouldn't be hard to do with numbers. We just know that we have this situation that before we had I, A, omega A, plus I, B, omega B, and afterwards they've stuck together, so we have I, A plus IB, omega final. So if I want to solve for this, that final, for the sake of having a little more room to write all omega final is simply going to be, what was the total angular momentum before? Divided by there we go. If you like, we could put in some numbers. Let's just make this up. Suppose that mass A is 10 kilograms. Its radius is, we'll make this 0.5 meters. Mass B, it's 4 kilograms. Its radius is 0.2 meters. We can go from there. Let's do it. We know that the moment of inertia for a solid disk is 1/2 mr squared. So we have 1/2 10 times 0.5 squared. And I'm making this up as I taught you, so I'm going to grab a calculator. 0.5 times 10 times 0.5 squared. And that comes out to be 1.25. We're going to assume we have 2 digits on everything. So we'll carry, I'm going to erase this for right now. We'll carry everything to 3 digits, 1.25 kilogram meters squared. It's going to be 1/2 4 0.2 squared it only has 0.080 kilogram meters squared. If I add that, well, I don't want to add those yet, but later when they're stuck together, .25 plus 0.08. It's going to be 1.33 kilogram meters squared. All right. Let's assume that omega A, that first one, is rotating at 80 radians per second. The smaller one is actually spinning much faster. We're going to say it's rotating at 160 radians per second. This one has the speed advantage, but this one has a considerably larger moment of inertia. And let's just see, how fast will the system be going afterwards if these now come into contact with each other? So let me write everything down so we have a little bit of room. IA is 1.25. IB 0.080. So here we are. Conservation of momentum. Angular momentum is just I omega. So we've got 1.25 times 80 plus 0.080 times 160 equals, after they stick together, it's 1.33 omega final. So omega final, remember what it said. It said it was I omega A, so it's this plus this, but it looks the same. Let's just do the numbers real quick. 1.25 times 80 plus 0.08 times 160 divided by 133, and our final is going to be 0.85 radians per second. You'll notice that the final velocity is much closer to the A's than B, and that's because this one had a much larger moment of inertia. 1.25 is considerably larger than 0.08. All right, let's keep going. If I can draw this next problem well, I'm going to try to draw it well. Consider a horizontal surface. And on this, I'm going to change how I'm drawing it. There's a string, and in this string, there is a small mass moving a little block. It's moving on a horizontal, in a circle, and it's resting on top of a horizontal platform of some kind. All right, since the block slides on a frictionless surface, V1 with a speed of V1 and a circular path radius R1. So we've got a frictionless surface, that's important. It's moving as a mass M, and it has an initial velocity V1 or VI, and it has, they don't give us an actual number, and it has initial radius called Ri. All right, if you pull the string from underneath here, it's going to change its radius. And suppose you change it so that you have a different radius. In fact, you shorten it to half of its original. How is that going to change this speed? If you pull the string and you shorten the radius, well now first of all, we really want to talk about and decide, if I pull that string, I'm an external object, I'm not part of this system. Am I going to exert a torque on it? Well, let's think about what it takes. The object is moving in a circle. If I pull on the string, let's think about the tension here. The tension in this string is directed towards the center. That's the force that keeps it moving in a circle, right? It's that tension in that string. However, if I pull on this string, I'm exerting a force towards the center when I shorten it. Does that exert a torque? I don't think so, because I'll be applying a force in the direction of the lever arm. There won't be any, when I try to do the torque formula, if I pull on the string, that angle will be in the direction of the tension. I don't exert any torque. In other words, think about it like this. Pulling on that string does not cause a tendency to rotate. Doesn't want to cause it to rotate faster in either direction. We'll assume for now that it's rotating this way simply so we can have a positive torque. But pulling on this string does not affect its tendency to rotate. All it's doing is shortening the lever arm. But if I pull in the direction of the lever arm, I got no torque, okay? All right, so I'm not going to exert, even though I feel like that is an external force, it doesn't exert a torque, so I should have conservation of angular momentum. All right, angular momentum basically says the initial has to equal the final. Now, for a point mass, this is really interesting. We know we think of this as being I omega. What's the moment of inertia for a point mass? For a point mass, the moment of inertia is mr squared. So this again would be the initial, but that's the moment of inertia. Omega, if we go back to that relationship between angular and linear velocities, you will remember that V equals R omega, or omega equals V over R. If I put that in, and again, these are all the initial ones, this side is going to simplify down to MVR. I mention that because for a mass, a point mass, moving in a circle or even moving in a straight line relative to some point, its angular momentum is mvr. That's the angular momentum of a point mass. It's, of course, exactly equivalent to its moment of inertia times its angular speed. All right, so we're left with mv1r1. This side is exactly the same. We see that masses obviously don't change. So our final, I use i's and 2's, so let's change these to finals. V final is simply going to be V initial times R initial over R final. In this case, R final is R initial over 2. Notice how the R's are going to cancel. You'll be dividing. It's going to be 2V initial. If you reduce the radius to half, you're going to have to double the velocity. You can look at this in this relationship. It's really obvious, right? Velocity and the radius are essentially inversely proportional to each other. If you halve the radius, you're going to have to double the velocity to maintain your linear momentum. Okay, there were some interesting things, but I kind of want to think about that. There's a part 2 that says what happens if you let outstring, same problem. So the vinyl radius is equal to 2 times the original radius. Oh, and they want us to find the tension. Hadn't looked at this problem. Let's think about it. Well, we know that the tension in this case provides the centripetal force. And centripetal force, of course, is m v squared over r. So this would be, put an I there. That's the initial tension. The question really wants to know what happens to this tension if you double the length of the string. So let's think about that. If I double the length of the string, let's go back and use our conservation of energy, of linear momentum. I know m v I r I. I know sometimes I'm using capitals and sometimes I'm using lower, but they don't matter in this problem. If I double this, where it's twice as much, I can see that the final velocity is simply equal to, the RI's cancel, the initial velocity divided by 2. In other words, that makes sense. Before, when I halved the length of the string, it doubled the speed. If I double the length of the string, it obviously halves the speed. So I just need to put this in over here. The tension is VI over 2, my final speed. And then, of course, this is also was doubled. So I've doubled the radius. I've halved the speed. That comes out to be mvi squared. That's going to be over 4. That's going to go down here. So what you see is by letting the string out twice as much, my tension actually falls to 1/8 of the original tension. Okay, so it's just kind of a fun one to play around with. How does changing something in a formula affect things compared to the original? We got this really easy with our linear momentum, our angular momentum. If you double the radius, you're going to halve the velocity. If you triple the radius, you're going to third the velocity. When we come over here, of course, we have to change both the velocity and the radius, and we got that down to 1/8. Let's do one more problem. I wish I could demonstrate this personally, but I can't. But suppose you have a person and they're standing on a platform that is free to rotate. And we're going to assume it's rotating without any friction and make it very ideal. If I had 2 dumbbells, and I actually have 2 dumbbells, I could go get some. We'll pretend markers are dumbbells. If I hold them out here, my moment of inertia is going to be larger than if I pull them in right here. Well, you've seen this with ice skaters. When their arms are out here, they have a larger moment of inertia. When they pull them in, all of a sudden they spin faster. They're spinning faster because of conservation of angular momentum. So let's look at an example. Here's our person. We're going to have a little stiff person. And he's going to start off with his hands extended, holding his little dumbbells. Standing on this rotating platform. He's spinning right through the center of his person. All right. We have 2 5-kilogram dumbbells. And they are a distance of 1 meter from the center of rotation. So he's got a longer arm than I do. He's a lanky guy. From the center of rotation to where he's holding the dumbbells, that's 1 meter. He's revolving with an angular speed of 0.5 revolutions per second. All right. They also tell me that the moment of inertia for the man is 3 kilogram meters squared. It's a pretty small number because most of his mass is very, very close to the center of rotation. Remember, to increase moment of inertia, you need mass to be far away from the center. He's probably actually standing with his feet together. So, all right, we need to get the moment of inertia for the dumbbells. Well, this is just like we treat the dumbbells in this case as point masses. Anytime the mass is fairly concentrated compared to this distance, we can treat it like a point mass. If I was going to calculate the moment of inertia for the Earth as it revolved around the sun, I would treat the Earth like a point mass because all of its mass is very concentrated compared to the distance between the Earth and the sun. I can certainly treat these 5-kilogram dumbbells as point masses. They're sufficiently far away from the center. Okay, so for point mass, we just use mr squared. So I have 2 of them, so it's going to be 5 times 1 squared plus 5 times 1 squared. And we see for the dumbbells, that just comes out to be 10 kilogram meters squared. So for the whole thing, I is going to be 13. 3 kilogram meters squared, 10 kilogram. So we have a moment of inertia, 13 kilogram meters squared. All right. Then it says, when he brings his arms in, R is reduced to about 20 centimeters. So say it's going to bring them in. Oh, it's going to change more than that. So we just want to find, okay, that's kind of the before. I'll stop right there. So we have somebody with this much moment of inertia, the 13, and he's revolving at 0.5 revolutions per second. When he pulls his arms in, so let's draw that picture. So he's got them pulled in like this. We have everything changes except a little bit. So we have the 2 dumbbells, they're 5 kilograms. But now they're at a radius of 0.20. you're going to have a much smaller moment of inertia. The man also, it changes his moment of inertia because he brings in his hand. So he has a moment of inertia now that's dropped down to 2.2 kilogram meters squared. That makes sense because when he was like this, the mass in his arms was fairly far away. When he brought it in closer, that brought down his total moment of inertia. All right, so let's do the moment of inertia for the dumbbells is 5 times 0.2 squared plus 5 times 0.2 squared. And it came out to be 0.4. So now our total is only 2.6 kilogram meters. That's a pretty dramatic switch from 13 down to 2.6. All right, let's look how that's going to affect conservation of momentum. Conservation momentum says I initial omega initial equals I final omega final. Now, we usually like things to be in SI units, but truthfully, if you look at this, it doesn't really matter what unit omega is in this angular velocity. Whatever unit we have here, that's the unit we'll get here. We can leave this as 0.5 revolutions. So I've got 13 times 0.5 has to equal 2.6 times omega final. So let's do the math. 13 times 0.5 divided by 2.6 comes out to be 2.5 revolutions per second. So his moment of inertia dropped to 1/5 of what it had been. So his angular speed is now 5 times faster than what it was. All right, we have one more idea. We're not going to go greatly in depth in this idea this year. It's a good topic. We just have limited time. And that's the idea of what does it truly mean to be in equilibrium if we're no longer talking about a point mass? What if we're talking about a rigid body? Let's think about this. Normally, if we were just thinking about a point mass, we would consider equilibrium to be the place where all the forces were zero. When all the forces were balanced, we thought the object was in equilibrium. However, if we're talking about a rigid body, something that takes up space, that could rotate, we also need the sum of all the torques to equal zero. Because even if all of the forces are equal to zero, it's still possible for the object to rotate. Very simple. Here is a board sitting on a fulcrum. Let's suppose it's balanced. If it's perfectly balanced and this board weighs 10 newtons, then the fulcrum pushes up 10 newtons, we're set. Okay, what if I tell you that I'm going to put a force here and I'm going to put another force here. And if those two forces are equal, we'll let them be 10 newtons. We'll let this be 2 meters to the center of the board, 2 meters again. what you'll notice is the sum of the forces is still 0. A 10 Newton force pushing down and a 10 Newton force pushing up, they're balanced. But that's not going to be in equilibrium, because if I apply a downward force here and an upward force here, this thing's going to want to rotate counterclockwise. Okay? That's not in equilibrium. In fact, let's go ahead and say that. If I said, what's the torque here? Well, the torque due to A is going to be 10 newtons times 2 meters. And the torque due to force B is also 10 newtons times 2 meters. That's 40 Newton meters of torque. Presumably, if the center of mass was here, and let's say that this really was, I don't know, a light board that weighed 10 newtons, you would have also, right here, 10 newtons pushing down due to the weight of the board, and 10 newtons pushing up due to the fulcrum. That'd be balanced. Those two don't exert any torque because they're both located right at the point of rotation. The center of mass of the board is going to be at that pivoting point. So, but anyway, you can see you're not in equilibrium. Let's change it. Let's push down here. Now what we see is A is going to be a clockwise torque, 10 newtons times 2 meters. But B is, a counterclockwise torque still. A is counterclockwise. B will be clockwise. That will make this be negative. That's going to change the net torque to be 0. This one's trying to make it rotate counterclockwise. This one's trying to make it rotate clockwise. It's also going to do something else. It's going to change the force applied by the fulcrum. If I look at the sum of all of the forces, there aren't any horizontal forces that I've drawn, but vertically, what's pushing the downward forces are now the 10 newtons from A, the 10 newtons from B, and the 10 newtons for the weight, this weight right here, which means that the fulcrum will now push up with 30 newtons. Okay, but it will do that. The fulcrum will respond. So if I picture this, we've got 3 different downward forces. We've got the weight of the board, force A, force B, but that would be static equilibrium. Nothing would move. Okay. It's not enough for the forces to be balanced. We also have to have the torques be balanced. If the torques aren't balanced, an object will tend to rotate, even if it's not going to translate. All right, so that's the end of this video. We'll definitely work for more problems in class. I know that sometimes this point of chapter 10, we start to feel like it's a little overwhelming.